Space is not empty but filled with a superfine form of matter generated by mass defects throughout the universe. This insight transforms our current understanding of the cosmos.
Gravitational lensing. Standard understanding. Gravitational lensing is a phenomenon where the light from a distant celestial object, such as a galaxy or quasar, is bent around a massive object like another galaxy cluster or a black hole. This bending of light is a consequence of the curvature of spacetime around the massive object, as described by Albert Einstein's general theory of relativity. The effect causes the light to appear distorted, magnified, or even duplicated, enabling astronomers to observe objects that would otherwise be too faint or distant to detect. Joseph George's non-relativistic explanation. Joseph George presents an alternative, non-relativistic explanation for gravitational lensing based on his theory of space-filling matter resulting from mass defects. Here's an in-depth look at his approach. Space-filling matter concept. Mass defects. George introduces the idea that mass defects, the discrepancies between the actual mass of atomic nuclei and the sum of their constituent protons and neutrons, transform into an extremely thin form of matter that permeates the entire universe. Dense regions around massive bodies. This space-filling matter is attracted to massive objects due to gravitational forces, forming dense regions or bubbles around these bodies. Every massive entity, from the Moon and Earth to the Sun and galactic centers, possesses its own dense bubble of space-filling matter. These bubbles can overlap, with smaller bubbles nested within larger ones, e.g., the Moon's bubble within Earth's. Density gradient and refractive index. Higher density near massive bodies. The density of space-filling matter is highest near the massive object and decreases with distance, creating a density gradient around the object. Impact on refractive properties. This varying density affects the refractive index of the surrounding space. A higher density corresponds to a higher refractive index, meaning that light travels more slowly in these regions. Mechanism of light bending. Refraction of light. As light from a distant source passes through regions of varying density, and thus varying refractive indices, around a massive object, it slows down and changes direction, similar to how light bends when passing through mediums like water or glass. Cumulative effect. When light traverses multiple regions with differing densities, each with its own refractive index, the cumulative effect results in the observed bending of light, leading to phenomena like gravitational lensing. Implications of the model. Alternative to general relativity, George's model offers an explanation for gravitational lensing without relying on the curvature of spacetime. Instead, it attributes the bending of light to interactions with space-filling matter. Variable speed of light. According to this theory, the speed of light is not a universal constant but varies depending on the local density of space-filling matter. This contrasts with Einstein's assertion that the speed of light in a vacuum is constant for all observers, regardless of their motion. Compatibility with Newtonian gravity. The model maintains compatibility with Newtonian gravity, which describes gravity as an attractive force between masses, rather than a geometric property of spacetime. Summary. Joseph George's non-relativistic explanation of gravitational lensing attributes the bending of light to the varying refractive indices of space-filling matter surrounding massive objects. By modeling space-filling matter as a medium with a density-dependent refractive index, his theory provides an alternative mechanism for gravitational lensing that does not involve spacetime curvature as posited by general relativity. This approach challenges conventional understanding and offers a different perspective on how light interacts with mass in the universe.